Hi friends, welcome to Honesty Technologies. This is Santosh Tilak and you are watching Java Virtual Machine. We have learned about Java introduction, class and an object in Java which is covered in my previous classes. The Java Virtual Machine is a virtual machine that enables a computer to run Java programs. The JVM has two primary functions which are to allow Java programs to run on any device or operating system. This is also known as the write once, run anywhere principle, and to manage and optimize program memory. To load and execute, we will create one Java file with filename .java. Here, .java is the extension. We will compile with javac space filename.java, where C is a compiler in javac. Now I want to execute the Java file with java space filename. Filename you can create on your own. I will call the class with the help of Java command. I have created JVM's instance. Virtual machine. A virtual machine is a virtual representation of a physical computer, and the physical machine they run on is referred to as the host machine. A single physical machine can run multiple virtual machines, each with their own operating system and an application. C and C++. These are compiled languages. Code is first compiled into a platform-specific machine code. Once compiled, it is run only on platform or machine which is planned to run. Whereas Java or Python, instructions are executed directly without having to compile them. Java uses the combination of both techniques. Code is first compiled into a bytecode to generate a class file. This class file is often interpreted by the Java virtual machine for underlying platform. The same class file is executed on any version of JVM running on any platform and operating system. JVM creates an isolated space on host machine. The space can be used to execute the Java program irrespective of platform or operating system of the host machine. Now we'll see clearly JVM architecture. We have a class loader, runtime data area, execution engine, and JNI, Java Native Method Interface, and finally we have native method library. Class loader prepares the Java classes and loads them into main memory. Runtime memory or data area holds the runtime variables and data that is required to run in a program. Execution engine executes actual Java program when we run Java command with the Java class file. The execution engine looks for main method and execute that file. Class loader. When you compile Java source file, it gets converted into a bytecode as a .class file. When you try to use this class in a program, the class loader loads into a main memory. First class loaded into a memory is usually the class that contains the main method. Three different phases of class loading process: loading, linking, and initialization. Loading involves taking bytecode or binary representation of a class or interface with a particular name in generating the original class or interface from that. There are three built-in class loaders available in JVM: Bootstrap class loader, Extension class loader, and Application class loader. Bootstrap class loader. This is the root class loader. It is superclass of extension of class loader. It loads standard Java packages like java.lang, java.net, java.util, java.io, etc. These packages are present inside the rt.jar file and other co-libraries inside JRE pip directory. For example, when you print something in Java, you write system.out.print. The system class here is loaded from java.lang package. Now, we don't have to do anything explicitly to load this. It automatically loads by the Bootstrap class loader. Next, we have extension class loader. It is subclass of Bootstrap class loader and the superclass of the application class loader. This loads the extension of standard Java libraries which are present in the JRE extension folder. Loads the file present in the $java /home JRE /lib /ext directory. Consider that you have Java extensions which has ODB connector or JDBC connectors present inside your extension folder. Extension class loads these libraries into JVM. Next, we have application class loader. This is the final class loader. It is subclass of extension class loader. It loads the files present on the class-path. By default, the class path is set to the current directory of the application. You can also modify the class path by adding the parameters -class path -cp on the command line options. The JVM uses the classLoader.load class method for loading class into memory. It tries to load the class based on a fully qualified name. If a parent class loader is unable to find a class, it delegates the work with the child class so that Bootstrap class loader tries to load a class. If it's unable to do so, it delegates to extension class. If extension class is not able to load the class, delegates to the application class loader. If the last class loader is also not able to load the class, it throws a no class load or error class not found exception. After a class loaded into memory, it undergoes into linking process. Linking as a class or interface involves the combining different elements and dependencies of program together. Linking includes the following steps: verification, preparation, and resolution. Verification. This phase checks the structural correctness of the .class file by checking it against a set of constraints or rules. If verification fails for some reason, we get a verify exception. For example, the code has been built using Java 11 version, but the system has Java 8 version installed. The verification will fail. Preparation. In this phase, the JVM allocates memory for the static fields of a class or interface, that is, initialize them with default values. For example, let us assume that I have declared a Boolean variable in a class which says private static final Boolean enabled is equal true. Getting the preparation phase, the JVM allocates memory for the variable enabled and sets its value to the default value for a Boolean which is false. Resolution. In this phase, symbolic references are replaced with direct references present in the runtime constant pool. For example, if I have a references to other classes or constant variables present in other classes, they resolved in this phase and replaced with actual references. This is an optional phase and it really depends if you have some resolution to be done in a class files or not. Third one, initialization. Initialization involves executing the initialization method of a class or interface known as cl.int. This can include calling the class constructor, executing the static block, and assigning the values to all the static variables. This is the final stage of class loading. For example, when we declare the variable enabled in the previous example, it was set to its default value is false during the preparation phase. In the initialization, the variable is actually assigned of true. Note that JVM is multi-threaded. It can happen that multiple threads are initialized the same class at the same time. It leads to concurrency issues. We need to handle threads safety to ensure that the program works properly in a multi-threaded environment. The runtime data area has five different components. We have method area, heap area, stack area, PC register, and native method stack. Let us look them in detail. Method area, which contains all the class level data such as runtime constant pool, field, and method data, and the code for methods and constructors. If the memory available in the method R is not sufficient for the program startup, the JVM throws as out of memory error. The method area is created on the virtual machine startup and there is only one method area per JVM. For example, assume that we have a class definition where we have class called employee with two variables, string name and int age. We also have public constructor for employee which takes these two variables and creates a new instance of employee. In this example, the class level variables such as name and age in the constructor details are loaded into the method area. Next, we have heap area. All the objects and their corresponding instance variables and arrays are stored here. This is the runtime data area from which memory for all class instances and arrays is allocated. The heap is created on the virtual machine startup and there is only one heap area per JVM. Employee EMP is equal to new employee. This is one example. So in this example, we have a code for creating a new instance of employee object. In this example, instance of employee is loaded into the heap area. Stack area. Whenever a new thread JVM is created, a separate runtime stack area is also created. All local variables and partial results are stored here. For every method call, one entry is made in the stack memory, which is called as stack frame. The stack frame is divided into subparts, local variables and operand stack. For example, let us see the following code. There are two functions here. One function which takes in a list of answers and gets the score from answer. It then normalizes the score. Second function is normalize score, which takes in a score and returns the normalized score according to some maximum and minimum score. This example, the variable like answers are placed in the local variable array. Operand stack contains the variables and operators in the mathematical calculations and divisions here. Next we'll see PC register. PC register, program called register. The JVM supports multiple threads at the same time. Each thread has its own PC register to hold the address of the currently executing JVM instruction. Once the instruction is executed, the PC register is updated with the next instruction. Native method stack. The JVM contains stacks that support native methods. These methods are written in a language other than the Java programming language, such as C and C++. For every thread created, a separate native method stack is allocated. Execution engine. Once the bytecode has been loaded into the main memory and all the details are available in runtime data area, the next step is to run the program. The execution engine handles this by executing the code present in each class. However, before executing the program, the bytecode need to be converted into machine language instructions. The JVM can use interpreter or JIT compiler for the execution engine. Interpreter. Interpreter reads and executes the bytecode instructions line by line. Due to this, the line by line execution, the interpreter is comparatively very slower. Disadvantage of interpreter is when a method is called multiple times, every time a new interpretation is required. Let us look into this code. Here we take a variable called sum and then run a loop from 0 to 10 to increment the sum. In this example, an interpreter will fetch the value of sum from main memory for each iteration in the loop. It will then add the value of I to it and write it back to the memory. And it's very expensive operation because accessing the memory each time is expensive. JIT compiler. The JIT compiler overcomes the disadvantages of interpreter. The execution engine first uses the interpreter to execute the bytecode, but when it finds some repeated code, it uses the JIT compiler to compile the entire bytecode and change it to native machine code. This native machine code is used directly for repeated method calls, which improves the performance of the system. The JIT compiler has the following four components. The intermediate code generator. It generates the intermediate code. The code optimizer. The code optimizer takes the intermediate code and optimizes it for better performance. The target code generator takes the optimized code and converts that to native machine code. Finally, there is a profiler, which finds the hotspots in the code. These hotspots are code pieces that are executed frequently and repeatedly. Let us take an example. We have some variable which was updated inside the loop. The JIT compiler recognizes that the code has a hotspot loop which updates the variable repeatedly. So it tries to optimize the code. It takes a local copy of some variable in the PC register. Now, inside the PC loop, it works on the local copy and updates that. Once the loop is completed, it takes the local copy and writes back to the memory. Now, unlike the interpreter way, it does not access the main memory frequently. All actions and all operations done on the local register, which is much faster. This is what makes the JIT compiler better that code is.
Next, we have
Garbage collector. The garbage collector collects and removes unreferenced objects from the heap area. It is the process of reclaiming the runtime unused memory automatically by destroying them. Garbage collection makes memory efficient because it removes the unreferenced objects from heap memory so that it makes more free space for new objects. Garbage collection involves two phases, mark and sweep. In mark phase, garbage collection identifies the unused objects from memory. In sweep phase, garbage collection removes the objects that were identified by the previous phase. Garbage collections is done automatically by JVM at regular intervals and does not need to be handled separately. You can also manually trigger garbage collection by calling system.gc Java native interface. Sometimes it is necessary to use Java native or non-Java code in Java programs. It can be for a case where you need to interact with hardware or to overcome the memory management and performance in Java. Java supports execution of native code via Java Native Interface (JNI). JNI acts as a bridge for permitting the supporting packages for other programming languages such as C and C++, etc. This is especially helpful in cases where you need to write the code that is not entirely supported by Java, like some platforms specific features can only be written in C. You can use the native keyword to indicate that the method will be provided by the native library. These are the libraries use method library. These are the libraries that are written in other programming languages such as C, C++, and assembly. These libraries are usually present in the system in the form of DLL or SO files, depending in the platform you're working on. These native method libraries can be loaded using JNI. Finally, we have summary. JVM allows Java to follow the write once, run anywhere approach. Java is a combination of compiled and interpreted languages. Code is first compiled into bytecode and then interpreted by the Java virtual machine. JVM consists of a class loader, runtime data area, and an execution engine. The class loader loads the program into main memory. The runtime data area holds the variables and partial outputs required for execution. The execution engine runs the final Java program. You can run non-Java code in a Java program using Java Native Interface (JNI). Finally, we have learned about native method libraries that are written in other programming languages such as C and C++ and assembly. In the upcoming videos, we are going to look how access modifiers work in Java. Hope you like my videos. Please comment. Please subscribe to the channel.